What do we see when we look up at the stars? When we can see them? What do they mean to us? Are they just a lovely backdrop to our earthly pleasures? A chat round a fire? Lying on a beach? A drink with a lover? Do we perhaps wonder at what worlds may be circling them, from which eyes may be looking back at us? Are they ordinary? Could we ever see the stars as our forebears did, as the faces of gods making daily and yearly traverses across the heavens, descending into the earth to fight monsters, to die and to be born again? Could we see the great beasts, their rearing forms perpetually in conflict with guileful hunters? These stories are ancient, yes, but more so even than you might think. They mark our species' first attempt to know its place in its bewildering world, an eternal reflection of the shifting travails of mortal life. For no star is this truer than for Sirius, the brightest star in the night sky. As well as being bright, it is one of the easiest stars to locate. The 3 stars of Orion's belt point directly towards it, and it forms a near direct line with the great red star Aldebaran. It is one of only 2 stars brighter than the planet Saturn. The other is Canopus, supposed home of Dune, which, given that Canopus is 1,000 times brighter than the Sun, could explain that planet's climate. To our celestially literate ancestors, Sirius would have been as obvious as a road sign. The earliest civilizations, almost without exception, bestowed Sirius with the name of dog. To the Greeks, Sirius and his brother Procyon were the hunting dogs of Orion. The Phoenicians called Sirius Barker, and other Semitic cultures, such as the Babylonians and Akkadians, appear to have referred to it as a dog as well. The association even made it into the first ever work of science fiction, a true story, by the 2nd century AD satirist Lucian of Samosata, in which his ship is caught in a waterspout and sent to the moon, with whom he engages in an interplanetary war against the forces of the sun for the rights to colonize Venus, aided by a phalanx of dog-headed aliens from Sirius, a joke Douglas Adams would reuse over a millennium later.
And a party of young conservatives from Sirius B. This is all your fault, of course.
Sirius's first appearance from behind the sun, its heliacal rising, signaled the height of summer to these first civilizations, which is why, even before it alliterated, we refer to them as the dog days. In an interesting counterpoint, Takurua, the Maori name for Sirius, was also their name for winter, since, of course, in their hemisphere, the seasons are reversed. But if you think the canine associations were limited to the Bronze Age cultural sphere, think again. To the Chinese, Sirius was Tianlang, the celestial wolf. To the Inuit, the moon dog. And to the Pawnee and Cherokee, the wolf star that guards the Milky Way or guides souls along its length. In Scandinavian mythology, Sirius is the dog of Sigurd, the deer slayer. Another common myth ties Sirius to an arrow pointing at Orion, shared between Sumerians, Persians, and the Chinese. And the dog is not the only totem that separate cultures have placed in our sky. Ursa Major, the great bear, to the Greeks was Callisto, who was turned into a bear by Hera and then nearly shot by her son Arcas. In Finnish tradition, the bear came from Ursa Major and was allowed to return when it was hunted and killed. Among the Iroquois of North America, Ursa Major was a bear chased by 3 hunters. To be fair, Canis Major does vaguely resemble a dog, more so at least than Ursa Major does a bear, but as much as, say, Scorpius resembles a scorpion? In that case, I can totally believe that the Maya may have independently thought that up. But for me at least, the association of Sirius with canines and Ursa Major with bears appears far too deep and widespread to be due to coincidence. But to be one story, spread across the world, it would have to have first been told before the ancestors of the Native Americans crossed the Bering Strait, 16,000 years ago. In the dog star, we may be glancing at a fragment of the dreams of our most distant selves. At this point, some of you are probably crying, "What about the Dogon?" All right, I will discuss the Dogon. Reluctantly. In 1976, Robert K.G. Temple published a book called The Sirius Mystery, in which he argued that the Dogon, a Malian tribe about 100,000 strong, possessed astronomical knowledge that wasn't available to Europeans until the age of telescopes. They knew that Saturn had rings, that Jupiter had 4 moons, and, most iconically, that Sirius was orbited by a tiny invisible star, so dense that all earthly beings together could not lift it. Temple did not get this information from the Dogon, of course. No, he relied entirely on the reportage of a duo of French anthropologists named Marcel Grioux and Germain Dieterlen, who had studied the Dogon in the 1930s. Leaving aside the fact that the Dogon are far from a lost tribe and that the above information was common knowledge by that time, Sirius B, as we shall learn, was discovered in 1862, while the rings of Saturn and the moons of Jupiter had been known for 300 years, Grioux was known to have something of a white savior complex, and wished to, quote, redeem African thought in the eyes of European scholarship. It later transpired that Grioux had relied on a single Dogon informant, who, when questioned, had never heard of any of these astronomical facts, leading to the fairly bleeding obvious conclusion that Grioux had made the whole thing up. And so, returning to the actual mythic past, of all ancient cultures, none raised Sirius higher than the Egyptians. To them, Sirius, or Sopdet, was the linchpin that held their world together, and upon which their ancient, unchanging culture depended. It was the earthly manifestation of Isis, the goddess of motherhood and protector of the kingdom. Her first appearance from behind the sun at the height of summer was as a gem on the crown of Ra, the sun god, rising from Duat, the underworld, on his celestial boat, having survived another night amidst the monsters of the netherrealm. For 70 days, which was also the period prescribed for mummification, both she and her husband, Osiris, astride the boat of Orion's belt, traveled beneath the earth. But when she rose again with the sun, then Khnum, the ram-headed god, awakened in his lair at the Nile's first cataract, and let loose the rush of the river's annual flood. In actual fact, the Nile's flood begins much further south, in the highlands of Ethiopia, when the summer rains flood Lake Tana and send a massive pulse of water 1,450 kilometers down the Blue Nile, before reaching the confluence of the Nile's other great tributary, the White Nile, still nearly 1,000 kilometers south of Khnum's cave. For the Egyptians, this inundation, and the black soil it left behind, was life. Their entire culture, their identity, was tied to it. To survive was to understand it, and to understand it was to understand the sun. The Egyptians were the first civilization to adopt a 365-day solar calendar, and the first appearance of Sirius from behind the sun, its heliacal rising, which, without fail, presaged the Nile's annual flooding, marked the first day of the Egyptian year. Except the Egyptians never corrected for the additional 6 hours of the solar year, meaning that the new year drifted slowly across the solar year, until, once every 1,461 years, it realigned with the rising of Sirius. The completion of the grand cycle, called the Sothic cycle after the Greek form Sopdet, was a holy event. Coins commemorating the cycle were embossed with the Bennu, the mystical bird called the phoenix by the Greeks, who, every 1,461 years, carried the egg of its rebirth from Arabia to the Temple of Ra in Heliopolis. Norman Lockyer, the astronomer who discovered helium in the spectrum of the sun, and who is widely regarded as the father of archaeoastronomy, noted that temples to Isis, the goddess tied to Sirius, were often built atop misaligned foundations to ensure that their altars always pointed toward the star's heliacal rising, even as the precession of the equinoxes knocked it out of alignment by 1 degree every 72 years. Greek culture lorded over pharaonic Egypt's for the last 300 years of the latter's existence. The Ptolemies, Greek-speaking descendants of one of Alexander the Great's generals, declared themselves pharaohs even before they knew what the word meant, absorbing what little of Egyptian culture they found of use and leaving the rest to the peasantry. This fuzzy intersection between cultures is particularly evident with Sirius, since, despite the name being of Greek origin, it is not entirely clear what it even means. Yes, the Greek word Sirios does mean glowing or scorching, but evidence is unclear whether the word was given to the star or the star was the source of the word. The mathematician Eratosthenes, who calculated the circumference of the Earth, describes certain stars as Sirius because of their brightness, and some have speculated that the name may have originated with Osiris. To the Greeks, Sirius was a far more malevolent force. Its searing radiance, when combined with that of the sun, induced the debilitating heat of summer. In his almanac Works and Days, the writer Hesiod declares that, quote, "In the season of wearisome heat, then goats are plumpest and wine sweetest, women are most wanton, but men are feeblest, because Sirius parches the head and knees, and the skin is dry through heat." Sirius's heliacal rising marked the roiling miasma of midsummer, when the malaria, or bad air, rose to afflict men with fevers. To be so afflicted was to be starstruck. The Romans sacrificed a dog on the day of Sirius's heliacal setting to prevent the star's fumes from inflicting crops with wheat rust. On the island of Chios, Greek stargazers watched for Sirius's heliacal rising as intently as Egyptians, not in expectation of a life-giving inundation, but to see if its flickering form augured a new wave of plague. If haze obscured its brightness, then illness was certain. The waves of summer heat caused atmospheric distortion at the horizon, and Sirius to scintillate from blue and white to red. According to the 4th century astrologer Hephaestion of Thebes, if Sirius was white at first appearance, then the flood would be high, but if Sirius was red, war was coming. This ties to one of the most infuriating historical mysteries regarding Sirius, the fact that so many classical sources describe it as red. Perhaps the most egregious example of this is Claudius Ptolemy. Not to be confused with the royal Ptolemies, Claudius Ptolemy was the author of the Almagest, the tried and tested astronomical treatise that formed the basis for astronomical inquiry from the time of the Roman Empire to the invention of the telescope. About as cast iron a source as you are likely to find. And yet, in his astronomical tables, clear as day, he describes Sirius as Kyros, reddish. Sirius, I hasten to add, is many things, but it is not, by any stretch of the imagination, reddish. Other stars Ptolemy declared Kyros included Aldebaran, Betelgeuse, and Arcturus, which are very red indeed. So clearly this was not meant as an equivocation. The Roman philosopher Seneca, too, described the stars of Canicula as red. Except Chinese sources from the time describe Sirius as white, which it is, and Ptolemy himself does not describe it as red in his second star catalogue, the Tetrabiblios. Any astronomical explanation falls foul of time. That kind of change takes millions of years, not thousands. So what gives? Was the Greco-Roman association of Sirius with heat and fire so strong that it colored their sight? Was Sirius observed so often at the horizon, where, as with the sun, the atmosphere can render it red, that the association stuck? There may be a simpler explanation. The Greek world was simply not as colorful as ours. Greeks associated color more with brightness than with hue. Homer called the bright sky bronze, the sea wine dark. Similarly, Sirius was bright and scorching, and so it was red. Sirius, perhaps unsurprisingly, would play a role in the transition between the cozy universe of the classical era and the staggering gargantuan universe of today. In 1717, Edmund Halley, of comet fame, compared the current positions of Aldebaran, Arcturus, and Sirius to those recorded in Ptolemy's Almagest, and found that they had drifted across the sky by a full 17 arcminutes, over a half a degree, in the intervening 15 centuries. The sphere of the fixed stars, which the ancients had considered the limit to human understanding, was in fact a horde, a river of 1 trillion radiant particles, sweeping us along in an eon-spanning voyage. This would mean, of course, that Sirius's title of brightest star in our night skies is and will only be temporary. 5 million years ago, Sirius was a nondescript faint star, a full 70 degrees from its current position. Sirius will continue its motion toward our Sun for another 50,000 years, brightening in our sky, until it passes by our system and begins to recede, growing dimmer. In 150,000 years, Vega will assume the mantle of brightest star in Earth's night sky. But all that raises a question. Just how far away is Sirius? The realization that the fixed stars are a swarm, not merely gems affixed to an adamantine sphere, led to the question of how to determine their individual distances. One heroic early attempt was made by the visionary cosmos wrangler Christian Huygens, discoverer of the rings of Saturn, who, in 1659, employed the newly discovered phases of Venus to rerun Aristarchus's experiment to determine the distance to the Sun. Correctly assuming that Venus and Earth were about the same size, he was able to fix the distance to the Sun to within 5% of its actual value. His attempt to extrapolate his success to other stars was inventive, if charmingly naive. Again, correctly asserting that the stars were merely distant suns, he assumed that Sirius and the Sun were of the same intrinsic brightness, their difference only due to distance. And since, according to his calculations, the Sun was 27,664 times the diameter of Sirius, it therefore had to be 27,664 times closer. In modern terms, this would place Sirius about halfway to the Oort cloud. If Sirius really was that far away, our species' conception of the universe would be very different. The first serious attempts to measure the distances to the stars began with the detection of parallaxes in the 19th century. I don't intend to go into parallaxes again here. If you want a detailed explanation of parallaxes and their role in determining interstellar distances, please see the previous video in this series, particularly the section on 61 Cygni, the first star to have its parallax measured. The man who measured that parallax was named Friedrich Wilhelm Bessel, a feat he failed to repeat with Sirius. Sirius's parallax was not accurately measured until the 20th century. Today, we know its distance is 2.637 parsecs, or about 8.6 light-years. One thing Bessel did notice about Sirius, and its brother Procyon, was a strange jig in their respective motions across the sky. The wiggle in their motion was exactly what would be expected if they were orbited by a stellar mass companion, except that no companion could be seen. In 1844, Bessel announced that, quote, "I adhere to the conviction that Procyon and Sirius are genuine binary systems, each consisting of a visible and an invisible star. We have no reason to suppose that luminosity is a necessary property of cosmic bodies. The visibility of countless stars is no argument against the invisibility of others." Unquote. A century before the dimmest flicker of understanding of the forces that power star life and star death, Bessel's assertion that some stars could be invisible, yet still have sufficient mass to affect luminous stars, feels prophetic. Nearly 2 decades later, in 1862, an American father-son team of telescope makers named Alvin Clark were testing a new lens by observing Sirius. Camille Flammarion, the 19th century French science communicator with a yen for the melodramatic, claimed that, upon glancing through the new lens, Alvin Clark the Younger cried, "Father, Sirius has a companion!" This is not attested elsewhere. The companion, now called Sirius B, orbited its primary every 50 years at a distance of roughly 20 AU, or Uranus's distance from the Sun. The discovery of Sirius B, or the pup as it was eventually affectionately known, allowed the mass of the Sirius system to be measured. Sirius was found to be almost exactly twice the mass of the Sun, a respectable if unspectacular size. Sirius B, on the other hand, was almost exactly 1 solar mass. In fact, it was slightly more massive. Upon noticing that Sirius B was half of its brother's mass, yet 10,000 times dimmer, Otto Struve, of the astronomical Struvas, see my previous video, concluded that they must be, quote, a very different constitution, unquote. No kidding. The Reverend Thomas Hussey, one of the first astronomers to speculate about the possibility of a planet beyond Uranus, pondered whether Sirius B might be a planet that shined by reflected light. Astonishingly, he was not the first to make such a claim, as a similar one had been posited over a century earlier by, of all people, Voltaire, in his sci-fi satire Micromegas, in which the titular Micromegas, a 40-kilometer tall humanoid, is exiled from his planet in orbit around Sirius and makes a journey to Earth, where, initially failing to detect intelligent life, he eventually falls into a conversation with a group of human philosophers, who all nearly die when Micromegas erupts in laughter upon hearing Thomas Aquinas' assertion that the universe was made for man. Being of cosmic proportions himself, Micromegas hails from a suitably gigantic planet, described as 21.6 million times greater in circumference than our own. Assuming an Earth-like density, a physical impossibility, but work with it, that would give the planet a mass of about 6 times 10 to the 46 kilograms, which is about 3 quadrillion times the mass of the Sun, or about that of your average galactic supercluster. It's amazing what your mind can conceive when unconstrained by knowledge. So, was Micromegas' Laniakea-esque homeworld a fair representation of what was actually found around Sirius? Well, no, but if anything, Sirius B was far stranger even than that. The real kick came in 1910, when Estonian astronomer Ernst Öpik measured its density, calculating it to be 25,000 times that of the Sun, a number he called impossible. This density is difficult for the human mind to grasp. At 1,000,000 grams per milliliter, it is 1,000 times denser than uranium. Arthur Eddington, the first person to experimentally prove Einstein's theory of general relativity, put it more poetically. Quote, "We learn about the stars by receiving and interpreting the messages which their light brings to us. The message of the companion of Sirius, when it was decoded, ran, 'I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox.' What reply can one make for such a message? The reply which most of us made in 1914 was, 'Shut up. Don't talk nonsense.'" Unquote. The reason for this turned out to be fairly simple. As many of you likely learned in high school, an atom is mostly empty space. But this statement severely undersells the reality. If an atomic nucleus was big enough to stand on, say a box a meter on a side, then the nearest electron would be 25 kilometers away. What these strange new stars, which would very soon be called white dwarfs, comprised was the matter of the atom with that empty space removed. Rather than the electromagnetic force that prevents your hand from passing through your desk, the particles in a white dwarf were held apart by the Pauli exclusion principle, a property of quantum mechanics that means that no two electrons can occupy the same quantum state. This is what prevents electrons from imploding down to the lowest orbital. But what force could create such a miniature monster in the first place? Eventually, theoreticians worked out that white dwarfs are the final states of stars like the Sun, or rather, within the same ballpark as the Sun, between, say, 0.5 and 5 solar masses. Stars lower than about half the mass of the Sun, which make up the vast majority of stars in the universe, churn their fuel so slowly that to date, none have ever died, though theory suggests they will become white dwarfs as well. A star, at every stage of its life, is a battle against hydrogen's desire to go down. It began as a disturbance in a great hydrogen cloud, likely caused by a supernova. As the pulse pushed more hydrogen into one place, its collective gravity grew, and pulled more hydrogen downward towards it. Eventually, the colliding hydrogen generated such temperature and pressure that it was able to fuse into helium, a process that generates vast amounts of energy. This energy then pushed against the weight of the falling hydrogen, creating a star. But eventually, the hydrogen in a star's core becomes depleted, and the weight of the hydrogen on top begins to press down again. The pressure in the core increases to gargantuan levels, sufficient to burn helium into carbon, and then carbon into oxygen. But with each fusing, the amount of fuel decreases exponentially, and soon the star has none left. For most of the stars in the universe, this is where the battle ends. A star reduced to a cinder the size of a planet, held up by quantum mechanics, slowly cooling into invisibility. For stars of between 5 and 10 solar masses, electron degeneracy pressure isn't enough to hold off the press of gravity, which crushes the star into a neutron star, 10 trillion times denser than a white dwarf. For stars much larger than that, gravity wins. Hydrogen goes down forever and becomes a black hole. In some ways, Sirius B is a fairly mundane dead star. Like 75% of its kind, it is a DA-type white dwarf, with a pure hydrogen atmosphere and an interior sorted by intense gravity into ever smaller layers of lighter elements, with most of its interior composed of carbon and oxygen. Its surface temperature of 25,000 kelvins, while 4 times that of the Sun, is also fairly average for a white dwarf. In one respect, though, Sirius B is remarkable. At 1.01 solar masses, it is one of the largest white dwarfs known. Its progenitor star is believed to have been over 5 solar masses, almost large enough to become a neutron star. For a time, when the dinosaurs ruled, the Sirius system would have been 2 bright stars in a tight 9-year orbit, though probably too distant to be visible in our skies. And what of Sirius itself? Well, it is about double the Sun in both mass and size, and an A-type star, the second rung above the Sun, which means it is 25 times more luminous. It is also the closest A-type star to the Sun, at just 8.6 light-years, 2 facts that combine to make it the brightest star in our sky. Perhaps counterintuitively, A-type stars possess little to no magnetic fields or magnetic activity, because the surging energy of their interiors crowds out any possible convection zone, the dynamo of stellar magnetic activity. Recent studies have suggested, however, that Sirius and Vega have shown minuscule surface magnetic fields of just 0.2 Gauss, though this is still double what Sirius's anemic convection zone is believed to be capable of generating, so its origin remains unclear. Thanks to the gravitational tug of Sirius B, Sirius rotates very slowly, just 16 kilometers per second, which is less than a tenth the average speed for an A-type star. Because of its slow rotation, the energy from its core is able to push light-absorbing elements, such as chromium and zirconium, up toward the surface, giving Sirius's surface an overabundance of these elements. The Sirius system projects a Stromgren sphere, a halo of ionized gas, as far as 2.6 parsecs into space. Collectively, the system produces a higher than normal amount of infrared radiation, much like the very similar star Vega, which means it likely has at least a dust ring, if not a ring of rocky material in orbit around it. Because white dwarfs cool at a relatively constant rate, it is possible to estimate the age of the Sirius system as a whole to be roughly 220 million years, with Sirius B existing as a white dwarf for about half that time. All of this together makes Sirius a highly unlikely home for life. Sorry, Voltaire, and V, but the chances of a sapient civilization existing around either Sirian star are essentially nil. For one thing, the system is barely 220 million years old. At that age, the Earth was only just laying down its oldest known rocks, and life had yet to evolve. Also, the turbulent history of Sirius B and its close interactions with Sirius during its main sequence life would almost certainly have torn any nascent planets apart, or even ejected them entirely upon B's becoming a white dwarf. None of this excludes the possibility of planets in the Sirius system, of course. Exoplanets have even been found around white dwarfs, but the chances of any of them being habitable are negligible at best. Sorry to end on such a downer note. I hope our lengthy stop around Sirius has not dampened your enthusiasm for the trip, which, come the next video, will be concluding its survey of the second ring, which includes such historic sites as Fomalhaut and Epsilon Indi. Hope to see you there!